In the next couple of weeks, we're going to be talking about empirical models, mathematical modeling, and regression models. And so I'm just going to kind of give you an introduction to empirical models in this screencast. Natural phenomena is described by some process. We have an input. This is also known as an independent variable or a factor or a predictor variable. This goes into some sort of process, whether that's a natural process or a synthetic or a chemical process, some sort of chemical reaction or mechanical process. And we have an output. This is known as the dependent variable. It depends upon the independent variable. Oftentimes we will refer to this as the response. And our job as engineers and scientists is to try to model this process. We try to put together some sort of mathematical model where we take into account the independent variable. There could be multiple independent variables going into this, by the way. And we try to come up with a prediction. This hat above the y represents the prediction or the estimate. And ideally, we would create this model such that the only difference between the model prediction and the actual output is just random error, denoted by this epsilon. We would like to determine the form of a mathematical model and the best values of the parameters in that model so that the errors are minimized in some sense and only represent purely random behavior that we are unable to predict. Models can take various forms. Some incorporate physical and chemical principles with adjustable parameters. These are known as fundamental models. Often it is expedient to use models that are simple mathematically, like linear or polynomial equations, and these are empirical models. Occasionally models are a mix of the two, and these are known as semi-empirical models. When choosing the form of a purely empirical model, it is important to make a selection that has a good potential of fitting the behavior of the data. The first step in choosing an empirical model is to look at the behavior of the process via collected data sets and depicted graphically. The simplest of models is a straight line, and many of you have seen the equation for this before. Our model prediction is some function of an intercept, beta naught, and a slope, beta 1. And the expansion of this model into a polynomial model to capture curvature in the data is most common. And here we have subsequent terms that incorporate polynomial terms, and we have the subsequent beta terms. For example, beta 2 is the coefficient for the x squared term. There are many other empirical models available, such as an exponential model, a power model, a logarithmic model. There are also some less commonly used models. We have an x reciprocal, y equals beta naught plus beta 1 over x. We have a y reciprocal, 1 over y hat is beta naught plus beta 1 x. We have an xy ratio, an x exponential. So there's lots of different candidate models that you can look into. The appropriate way to know whether one of these models is a candidate is to observe its behavior for different parameter values. Here we have an x exponential model, and depending upon the different parameters, b1 and b2, you can see that it can change quite dramatically. The remaining issue is that more than one model forms may be candidates for the data, so how do you decide which is best? You guys are going to learn in this class how to choose which model is the best for the data among several candidates. The assumption we make in specifying a model is that the mean, also known as the expected value, of the output variable, so that's mu y, is a function of the input variable. The mean of the output at any value of x is simply beta naught plus beta 1 x. That doesn't mean every time you put in the same value of x, you're going to get the same output. But if you were to look at the probability density function, it's going to be normally distributed about some value. That depends upon the value of x that you put into this model. Since y equals beta naught plus beta 1x plus some error term, epsilon, the expected value of epsilon is going to be 0. Epsilon is going to be a normally distributed variable centered about 0. X is sometimes called the regressor variable. The expected value of epsilon squared is the variance, is sigma squared, which describes the variance of y at any given value of x. So in the coming weeks, we're going to talk all about empirical models, how to create them, and how to analyze them.